Welcome back, everyone, to MATA35. We are going to be doing an introduction to regression analysis today. The first half of the lecture is going to be explaining sort of the ideas behind building linear models, and then the second half of the lecture will be on actually running stuff in Python. I will get to how we're going to run stuff in Python in the second half of the lecture, but don't worry, it should all work on MacBooks as well. It's all going to be online, and so you don't have to worry about running stuff locally. But let's go ahead and get started with what is regression analysis. And to answer this, I'm going to start with a very simple problem. What is the height of the CN tower? So now, suppose if you have a question like this in biology, one of the things you can do is you can go out and measure it, right? So let's suppose that, yesterday, you measured that the CN tower was 21,785 inches tall. Now, I'm going to ask you all a question. How tall will the CN tower be on July 15th, so a month from now? And these are your possible answers. Will it be 10,000 inches, 20,000 inches, 40,000 inches, or unknown? And so let's see. It looks like we're getting a lot of B's in chat. Okay, so somehow you guys all have in your heads built a model of the height of the CN tower where you're like, well, if I measure it once today, then a month from now, it really shouldn't be a different height. And so this is, in some sense, not even a linear model. This is the constant model. You're basically saying, my model for the height of the CN tower is that when I measure it, it always stays the same height. Okay, so that's all well and good. But now let's ask a slightly different question. Suppose instead I have a willow tree. And on June 15th, you measure that a weeping willow measures 424 inches tall. Actually, let me reset my chat here. So on June 15th, you measure that the willow tree is 424 inches tall. How tall will the tree be on July 15th? So I give a couple of different guesses here. Is it 212 inches tall, 424, 848, unknown, or none of the above? Let's see what people think. So we have a lot of people who are guessing 848 inches tall, a few people who are guessing unknown, and a few people who are guessing none of the above. And the answer to this, of course, is slightly more complicated, because somehow in our heads, we don't think that this is a constant model. Oh, it looks like a lot more people have guessed none of the above. We don't think that this is a constant model. Somehow we think that trees ought to grow, unlike the CN tower, which generally doesn't grow. But now, how much does it grow? Well, unfortunately, we now have two different things we need to know. We need to know how tall it is and how fast it grows. So there are actually two parameters here, not just one parameter. And so we don't actually know from just saying this, unless you happen to know how quickly willow trees grow. And you can look that up online, but as a biologist, one of the things you might be thinking is, well, what should I do instead? I could instead try measuring it again a little bit later or a little bit earlier. So if we had two different measurements, maybe that would tell us how quickly the willow tree grows and how tall it is right now. So let's reset my chat, and now let's suppose that we had two data points, because we have two parameters here. So on May 15th, so a month ago, let's say you measured that the weeping willow was 420 inches tall. And this month, you know that the same weeping willow tree is 424 inches tall. So now let's give another guess. How tall is the weeping willow a month from now, on July 15th? 420 inches, 424 inches, 428 inches, unknown, or none of the above? Okay, so you guys are all smart and you can figure out like the trend line. And so the trend here is basically, well, it seems like it grew 4 inches from May 15th to June 15th. And so, well, it really ought to then grow another 4 inches from June 15th to July 15th. And so a very good guess would then be 428 inches, because you've now built a model with two parameters, how tall it is right now and the rate of growth. Okay, but now let's go back a bit, and let's go back to our CN tower example. Suppose that you had no idea about the CN tower to begin with. Like someone just told you, oh, we measured some object that's in midair, and let's say that I measured that the CN tower is 21,786 inches tall on May 15th, and oh, sorry, And on June 15th, we measured that it is 20, oh, sorry, that's a misplaced comma, 21,785 inches tall. So the measurement we had yesterday. Now, how tall will the CN Tower be on July 15th? So will it be 21,784, 21,785, 21,786, question mark, or none of the above? Okay, so we're starting to get a couple replies in. Let's see what people think. Ah, okay. So we have a lot of question marks here. A few answers, and so we have a couple of people who are saying, well, it's going to follow the trend, and so it went down 1 inch from May 15th to June 15th, and now we think it's going to go down another inch between June 15th and July 15th, and a bunch of other people who are like, well, we don't really know, and so yeah, so the answer to this, and we have a question in chat, would it be C because it gets hotter in the summer and the meadow expands? So this gets at one of the really important points in modeling, so which we're going to make formal in a moment, which is basically we don't know what all parameters or what all variables actually make a difference in the height of the CN tower. And maybe there is a good reason that the CN tower sometimes varies in height, or maybe there isn't. And so, oh, it's number wrong. Yes, sorry, yeah, I have a typo here. Let me, the typo is basically 21,785. The comma was in the wrong place. But yeah, so the problem here is that we haven't been explicit about our model. Yes, so one possibility is that, as Samantha says, maybe the 1 inch is an error. So maybe while you're taking your little ruler stick and stacking it up all the way to the top of the CN tower, you made a mistake somewhere and you have a measurement that's 1 inch off. That wouldn't be too surprising since this is, after all, 5 significant digits. So that's a large number of digits, and it's quite possible you made a measurement error. It's also possible that you had a super accurate laser measuring device for the height of the CN tower, and it actually did change that 1 inch, and maybe the CN tower is slowly sinking into the ground. And in which case it would be 21,784 inches tall. And maybe like you might assume that there's some reversion to the mean. Maybe like it fluctuates with time. So like sometimes it goes up and sometimes it goes down. The real answer is we don't know. And what exactly it is depends on what model we're building. And this is a very important point because it really goes to show that when you're building a model, you can't just look at the data points and extrapolate from them. You have to have some underlying idea about how your system ought to be behaving when you're doing these kinds of predictions. Maybe if you have enough data, the data will give you some ideas, but here with just 2 data points, we're not sure whether our 2 data points actually show a trend or if it's just a measurement noise from error. And so both A and D would be very reasonable guesses here. Okay, so let's talk about that a little bit more. So the basic idea here is that we have different model assumptions. So for example, you might assume that the CN tower should stay a roughly constant height subject to experimental errors. So maybe you think that the CN tower doesn't grow up or like shrink down as time goes on. On the other hand, many people would assume that a willow tree does grow, and you might make the additional assumption that it grows linearly, subject to some experimental errors. These are all assumptions you can make, and of course you can make other assumptions, and depending on your biological model, the assumptions might be better or worse. If you collect enough data, it might hint at what the correct assumption is, but you don't know this a priori. So now let's go back to the CN tower. So we have this one parameter model. So the CN tower should stay a constant height. Oh, I have a lot of typos in this. There's an extra space in there. But anyway, subject to experimental errors. So if we want to model this mathematically, basically what we're saying is that the height over time is equal to b, where b is some constant. So the height of the CN tower doesn't change with time. So that would be an assumption. So that's a modeling assumption. And then we might say things like, okay, well, then maybe we have the height during May is equal to 21,786, and let's say the height in June is equal to 21,785. But if that's our model, of course, they don't quite match, because this implies that when we're trying to solve for this equation, b is equal to 21,786, but b is also equal to 21,785, and these two numbers are not equal. 786 is not equal to 21,785. Which is a minor problem, but one you've encountered before. And several of you in chat were already saying, well, it's probably just a measurement error. On the other hand, when we had the same same style of two measurements for the willow tree, it was actually a two-parameter model, and we had two data points. So let's go ahead and assign May to be equal to the 5th month and June to be equal to the 6th month, just so that we have numbers instead of names of months. Well, then what we have is h of 5 is equal to 420, which is equal to 5m plus b, because t is time, and time here is the number of the month, in our model at least. And we have h of 6 is equal to 424, which is equal to 6m plus b. When we solve these two equations, which you should know how to be able to solve, you get that m is equal to 4 and b is equal to 400, and so you end up with a prediction. So your prediction is h of July is equal to h of 7 is equal to 428 inches. Okay, since this is a two-parameter model, we don't end up with this contradiction that happens when we have two measurements. But now, of course, sometimes you might want more than two measurements. We have a question. Can we say the height of the CN tower is b plus or minus 1? Yeah, so that's another way of doing it. So there are very well-defined ways of talking about your measurement error. And we're going to be getting to some of that in a bit, but what we care about right now is less the measurement, the exact amount of measurement error, and instead what we care about is trying to build a predictive model. And for a predictive model, you often want to give both a single prediction as well as error bounds. But yeah, so that is one way of doing it. And in physics, that is one of the things that you will be learning. Here today, in today's class, we're going to focus more on constructing the model and less on doing the error analysis, which we might get to in Friday's class if we have time. But even for this two-parameter model, if you have 3 data points, then all of a sudden things can go wrong again. So let's suppose that you've taken 3 measurements. So on April 15th, you measured the height of 417 inches tall. On May 15th, you measured 420. I have so many random typos in these slides. I'm very sorry about that. A height of 420 inches tall. On June 15th, you measured that the same weeping willow is 424 inches tall. How tall is the weeping willow a month from now, on July 15th? So let me reset before you give answers. So what's your guess here? Is it 424? Is it 427? Is it 428? Question mark, or none of the above? So let's see what people are replying. Okay, so a lot of you, well, I mean, I've sort of led you to this answer, and a lot of you are guessing none of the above because we don't actually know exactly what it is, because we don't know the exact rate of growth anymore, right? Because one month it grew 3 inches, but the next month it grew 4 inches. So in this month, is it going to grow 5 inches maybe? Maybe that would be a quadratic model. Maybe it's growing 4 inches because maybe it was a measurement error the first time, or 3 inches. We don't actually know. And one of the questions you have as a biologist is, how do we build a good model when we have data that looks almost right, but it isn't quite exactly right? Now, when we were solving systems of equations 2 lectures ago, or 3 lectures ago, several lectures ago, one of the things we said is that, well, sometimes you have inconsistent systems of equations and then there is no solution. But when you're a biologist and you're measuring data, your data is always going to be inconsistent. The question is, how inconsistent is it, and what is the closest model that fits all of your data? And this is the whole point of things like regression analysis, is to find the best fit model. So now let's go back to the CN tower. So we're going to try to find the best fit model for the CN tower. So now, what does it mean for a model to be good? A model is good if it predicts future data accurately. But unfortunately, we don't actually have any future data. So when we build a model, we build it to accurately explain or fit to existing data. So let's suppose we've taken a bunch of measurements of the height of the CN tower. So let's say we have we've gone out with our yardstick and measured it every single month: January, February, March, April, May, and June, and we get slightly different results. So now let's go ahead and assume, for the time being, that our model is actually constant. Maybe your assumption is that the CN tower actually does have a constant height, and anything else is an error. So maybe you assume that h of t is actually a constant height. But now what we need to do is, well, now we need to guess a particular height and then see how good of a guess it is. And one of the ways you can do this is by measuring how much error there is from a particular guess. So let's start with a bad guess and see how much error there is. So let's say that our guess is, let's put out the error when h of t is equal to 20,000. So let's suppose our first guess is that the height of the CN tower is 20,000 inches. Well, what happens here is you take the actual value and you subtract out your guess, because that's the value. Our guess is the same for every single time period, and you end up with 1,779, 1,787, 1,788, 1,786, 1,786, and 1,785. So that's a pretty big error. Does anyone in chat want to just put in chat a better guess for what the actual height of the tower is? So these are things you probably learned in high school even. So what are ways you can try to use all these different, combine all these numbers together and give a better guess for the height of the CN tower? Okay, yeah, so we have Connor and Ryan who have said averages. Yes, exactly. So we have several different estimators for this, and yeah, so we have a lot of people who are suggesting combine all of them and find the average. That's a really good idea. So let's combine them all and find an average. So I'm going to call this the mean. So this is the arithmetic mean, and so this is going to be the error as h of t is equal to 21,785. So I've taken the average of all of these, and we want to know what the error is from this. Okay, so if we do the same subtraction, we get minus 6, 2, 3, 1, 1, 0. And we have another guess as well, which is maybe it's the median instead. And that's also a very good guess. So what is the median? Well, we want to take the biggest number. So the biggest number is this one. The smallest number is, that's the smallest number, and this is the biggest number. Then there's those two numbers. And so the median is the average of 21,786. So that's the median. So Sam was suggesting the median. Well, let's see what happens when we do the median. So median, which is error as h of t is equal to 21,786. And when we do this, we find that the error is minus 7, 1, 2, 0, 0, minus 1. Okay, so it seems like both the mean and median seem to be like pretty good estimators, right? So they're a lot better than our random guess of just 20,000, and they both give relatively small errors. And then you might ask, well, which of them is better? Well, that depends on how you're going to define the goodness of errors, or like what errors matter. So it turns out that when we want to measure how much error there is total, we want to measure errors in both directions. So an error of minus 6 is also bad, and so an error of minus 6 and an error of 6 don't cancel out. So they're not supposed to cancel out, depending on for many purposes. So we want to minimize errors, but both positive and negative errors are bad. And so there are two very standard ways of going from a negative number and turning it positive. And these are the absolute value or squaring before summing the errors. So we can either use the absolute value or we can square it. And those are both very standard ways of turning a negative number into a positive number. So if we start with the error from the mean estimator, so 21,785, well, we have the absolute value error of absolute error of values is 6231110. And if we want, what we can do is we can sum them together, or we can take the average of these. So the average is going to be 13 divided by 6, which is about 2.16 repeating. And another thing you can do is you might take the square of it instead. So this is another standard procedure. So this is the squared error. And for the squared error, you're going to get 36,49110. And so this value is going to be 51 divided by 6, which is equal to 8.5. Okay, so those are ways that you can combine together all these errors. So these are the average absolute errors and the average squared errors, both of which are standard ways of figuring out how good an estimator is. So what about from the median? So from the median, we also have a absolute error. So the absolute error is 712,001. When you add those together and divide by 6, you end up with 11 divided by 6. So that's equal to 1.83 repeating. And we have a squared error of 49,14001. And the squared error is 55 divided by 6, which is equal to 9.16 repeating. Okay, so one of the things you might notice here is that for the case of using absolute error, let me use a different color. For the case of using absolute error, the median has a lower number than the mean. But for the case of using, let's use a different color, squared error, the mean had a better value than the median. Okay, and it turns out that this is actually the reason why we care about, well, one of the many reasons why we care about the mean and median is because they minimize the, respectively, the absolute value of the error, or summed together, or the squared errors summed together. So what we call the best estimator depends on the error metric. So for mean absolute error, which is more precisely given a bunch of data points and a guessed height b, the mean absolute error is just taking 1 over n times the sum of the differences, of the absolute value of the difference between the data point and the guessed height. And it turns out that for this, the optimal guess is the median. So if the middle element is odd, it is the middle element if it's odd, or it's the sum of the two middle elements divided by 2 if it's even. And similarly, for mean squared error, which is another common error type, what we're saying is that given data points h1 through hn and a guessed height b, we're taking the difference and we're squaring it, and then we're adding them all together and dividing them by n. And it turns out that in this case, the optimal guess is the mean 1 over n times just the average of all the different elements. Does anyone have any questions so far? So basically, what we're doing is we're trying to measure the error of a guess by looking at lots of different data points, and this is the reason why the mean and median are what we use for our guess, because they turn out to minimize different types of error that we care about in practice. Okay, so that's all well and good for this one parameter model where we're only guessing a single number. So that's stuff that you guys have covered before. Well, like what is the best estimator for a bunch of numbers? Oh, they're both called mean because of the average oh, wait. Did I do something? Oh, yeah. So, yes, that's a very good question. Why are they called the mean absolute and the mean squared error? So that is because that mean corresponds to the mean of all these absolute, so this part. So the mean of all the absolute values or the mean of all the squares. So that's why we call it the mean squared error, because you're taking the mean of something else. In the first case of the absolute values, and in the second case of the squared deviations. Occasionally, you might also hear a term, so let me go ahead and mention it. You might also hear a term root mean squared error, RMSE, which is just the square root of mean squared error. And there are useful dimensional analysis reasons why it's sometimes useful to take the square root, but because when you take the square root of a positive number, the ordering of the numbers doesn't change. And so minimizing the mean squared error is equivalent to minimizing the root mean squared error. But we'll get into that later, and you don't have to worry about it too much for now. This is just one of the things that you may see when you're actually doing data analysis. Okay, any other questions? Okay, so far so good. This is a one parameter model, but what happens if we have a two parameter model? So let's go back to the willow tree. So if we have a two parameter model, then maybe we want a linear model. And in a linear model, in order to define a line, you need two parameters. You need a y-intercept and you need a slope. Or you need 2 points, but then you need two parameters in order to define a line. And so the question is, what is the optimal value for both m and b that minimizes the error? Now, of course, oh, I have my 1-2s. Okay. So here are the heights we had from our different months of measuring the height of the willow tree. So here I've put in a couple additional measurements for January, February, March, and April. So we have a bunch of measurements now. And now our question is, how do we model, how do we find a linear model? So instead of just finding a single constant value, a linear model that approximates all of these. So let's try graphing out all these data points. So let's see. Let's see, this is month 1, 2, 3, 4, 5. Oh, need more space. 6. So those are the only months we have. And I'm going to do one of those silly things, and I'm going to have a big jump in my axis. And so this is going to be 400. And let's say this is 410. And this is 420. Actually, let me space these out a little bit better. This is 410, and let's say this is, oh, sorry, that's 400, 410, 420, and 430. Okay, and so we have a couple points here. So the first point is 1404, because that's January, the height was 404, so that's somewhere around here. Then we had 2407, so that's somewhere around here. We had 3412, so, come on, go back. Go back. I skipped forward way too far forward. Let's see, so we had 3412, so that's somewhere around here. 417, so that's somewhere around here. 420, that's around here. And 424, so that's somewhere around here. So what we're trying to do is we're trying to find a line that passes through all these points. But of course, as you know, these points aren't quite collinear, so there is no single line that passes through all the points. And so you might guess different lines. So for example, maybe you guess this line. Now this line isn't so great because you have all this error in each of the points. But maybe there are better guesses. So for example, if we guess, say, this line, this is actually significantly better because then their errors are a lot smaller. And so the question is, what line passes through, has the least error from both of these 2 points? And again, we can measure the error, we can measure the absolute errors, but there's both up and down, and so we need to measure the absolute error or the squared error. So we have these similar sort of formulation. So even though this is a linear model, we can still talk about the mean absolute error, which is given a bunch of data points. Here, instead of subtracting out the height, a constant height, we're subtracting out whatever this function says. So whatever this function predicts the value to be, we're going to substitute that in, and we're taking the error away from that line. And when we do this, that allows us to figure out the line that has the lowest mean absolute error. Unfortunately, this is kind of hard. Like, doing this computationally is, well, our computers can do it now, but this is a relatively hard problem. Let's see, we have a question. Should we make the line in the place where the error would be equal above and below the line? Not necessarily. So it depends on how you're, like, so this is sort of the point, right? There are all these different ideas of error. And depending on your model, you may care about one type of error more than other types of errors. What I'm giving you today is I'm giving you 2 different types of errors that you might care about. And in this particular case, for mean absolute error, yes, you want the total amount of error above and below the line. So it's not quite that you want them to be the same, but you just want the total amount to be minimized, both for the stuff above and for the stuff below. So they both are equally bad. And of course, we also have a similar formulation for mean squared error. So given those same data points, instead of taking the absolute value, we're again subtracting out the value of the data point from the prediction from the function, and we're squaring that value. And so in this case, the thing with mean squared error is it places more emphasis on points you get really, really wrong. So this is a difference in philosophy about like what types of errors you care about. maybe you're fine if your model makes lots of little mistakes, but you really don't like when it makes a really big mistake and lots of little mistakes. And you'd rather it make lots of medium-sized mistakes than one super big mistake and a bunch of little mistakes. And so that is, of course, a question. And depending on how you answer that question, you might decide to use the mean absolute error or the mean squared error, depending on which one you care about more. Now, I'm not going to get into model and error selection because that is a topic of a statistics or data science class, or just of a biological modeling class, which this class isn't quite, though we're trying to give you the tools to be able to do it. So we're going to focus for the remainder of this class on just the mean squared error, and there's a very good reason for, wrong way. There's a very good reason for this, which is that it turns out that the square function is nice because it looks vaguely like a parabola, and with parabolas, we can find the minimums of these functions using the tools from calculus that we've been discussing for the in the last lecture. So even though this is a multivariable parabola, you can still find the minimum of this function by making use of partial derivatives. Okay, but anyway, let me go ahead and show you what ends up happening at the end of the day. So let me show you what we get at the end of the day, which is at the end of the day, you get a function with, you solve for this, you get a function with that basically that almost passes through all these data points, and allows you to give a prediction for time 7. So we have this function, f of t is equal to about 4.11 t plus 399.6. So this is basically saying that our model is that the our model has a particular height for the willow tree at a particular point in time, and we're guessing that it grows at about 4.11 inches per month. So these are the parameters you end up getting when you solve for the minimum. And of course, with this data, you can guess that f of 7, so July, is equal to 428.37. 0.37. So July, 428.37 inches of predicted height. And intuitively, what we're doing now is we're basically taking this line and we're extending it out to the 0.7, and then that is our prediction. So that's basically what we're doing with this model, is we're trying to find the best fit line, and then we're using that to predict the next data point. Okay, any questions about all that? Okay, so that was all the sort of high-level modeling concepts. But how do we actually find these minimums of this two-parameter family of functions? Like, what is the minimum line? And it turns out, well, we're going to use multivariable calculus, which we studied last class, or last Wednesday and Friday. And let's walk through the derivation for a simple example, by which a simple example I mean for our willow tree. And unfortunately, this is going to look, even though this is a simple example, it's going to look super duper complicated. So the first thing we do is, well, we have to write out this function. So if we write out this function, this is the s of mb, which we're going to call this function, this MSE function. So let's call this MSE of mb. I'm just going to call it s for squared because it's, well, less writing to do. So s of mb. So this is the squared error for given parameters m and b. Okay? So this is the function of m and b because what we're asking is, given some parameters m and b, given a particular line, what is the error of the data points from that line? And when we do this, what we get is, well, time 1 is going to be, let's see, so this here is time 1, and this here is h1, and so on. So this here is h2, and this here is time 2, and so on. I made it super easy by making time 1 equal to 1, time 2 equal to 2, time 3 equal to 3, and so on. But in general, that may not necessarily be the case. So this is just because I made life easier for this computation. So when you do this, well, you have to plug in all these values. So this is going to be 1/6 times, well, what's plugged into the first one? So that's h1 and t1. So you have 404 for h1 minus m times the time 1, which is just 1, minus b squared. Okay, so that's the first term of that summation. and you take the second term of that summation, so that's 407. Since h2 is 407, time is now time 2, so this is minus 2m minus b squared. Oh, sorry, I shouldn't end the bracket because that's only two of our terms, and then we have another 4 terms to go. So plus 412 minus 3m minus b squared plus 417 minus 4m minus b squared plus 420 minus 5m minus b squared plus 424 minus 6m minus b squared. Okay, so now this is probably looking a little bit ugly. And it is a little bit ugly because we're working with actual data. But you'll notice that this is a two-variable function. And in fact, it's a two-variable function with some squared terms, but it's not actually that complicated. And if you were to simplify all of this, and yes, it would take a while to simplify all of this, you would just have a function of two variables, which you could then take partial derivatives of. In fact, you don't even have to simplify to take partial derivatives, and it's a little bit nicer to take the partial derivatives without simplifying. Let's go ahead and take the partial derivatives. So here we have ds del s del m, the partial with respect to m. So we're looking at m and b as variables along that we're taking partial derivatives along now. So this is going to be equal to 1/6 times, well, when you take a partial derivative, you can take a partial derivative with respect to each of the individual pieces, right? So, well, when you take the partial derivative of 404 minus m minus b squared with respect to m, well, that's going to end up being 2 times the partial derivative. Let me give myself a little bit more space. So you're going to use the chain rule, but so this is going to be 2 times 404 minus m minus b. And what's the derivative of the inside? The derivative of the inside with respect to m is minus 1, because m is because minus m has the derivative of minus 1. So this is actually going to be minus 2 times 404 minus m minus b. And in the next case, we also take the partial derivative with respect to m, so that's going to be 407 minus 2m minus b. And of course, it's squared, so you have a 2 there, but you also have a minus 2 factor from the inside, so it's going to be minus 4 times this. And for the next one, we have minus 6 times 412 minus 3m minus b, minus 8 times 417 minus 4m minus b, minus 10 times 420 minus 5m, minus b, minus b, minus 12 times 424 minus 6m minus b. Oh, can I explain the minus 2 again? Yeah, so let me write this to the side, actually. Give me a moment. Let me turn off my edge stat so I have a little bit more space. Okay, so basically the idea here is when you take dm of 404 minus m minus b squared, that's going to be equal to, well, you have the two from up there, right? So that's 2 times 404 minus m minus b times minus 1, because the derivative, because dm of minus m is equal to minus 1. Because of the chain rule. So that's because of the chain rule. Okay, does that answer your question? So basically, you're applying this partial derivative to each of the individual pieces. And when you apply to each of the individual pieces, that's a minus 1, sorry. When you apply it to each of the individual pieces, that's the value you end up getting. Okay, so this is the reason why earlier on in this class I told you all that you guys really need to be really comfortable taking derivatives and like integrals, because I'm just going to do them on the fly like I did in this derivation. Okay, so moving on, that's the partial derivative with respect to m. Well, and we also need the partial derivative with respect to b, right? So ds db. Well, what's that equal to? Well, now we're taking with respect to b and not with respect to m, and this is actually a little bit easier. So if we start with the 1/6 again, and for each of these things, the derivative of minus b is just minus 1, and we don't have the 2m, 3m, 4m, because we just have a minus b on each of them. So this is going to just be minus 2 times 404 minus m minus b minus 2 times 407 minus 2m minus b minus 2 412 minus 3m minus b minus 2 417 minus 4m minus b and minus 2 420 minus 5m minus b minus 2 times 424 minus 6m minus b. Oh, there's still confusion about the two. Let me put it slightly differently. So d dm of m plus 1 squared is equal to 2 times m plus 1, right? And so you also have d dm of 1 minus m squared is equal to, oh sorry, let me duck away, is equal to 1 minus m times 2 times minus 1 because of the derivative of the inside. Yep, yeah, no worries. Yeah, okay, good. Everyone's on the same page now. So yeah, so you just have to be really quick at taking these derivatives, even when they look a little bit funny. And so one of the problems that sometimes happens in starting calculus classes is you always take the derivative with respect to x or y. And so then when you see these other variables, you don't automatically think to take the derivative with respect to them. And so you do need to be a little bit careful. Yeah. Okay, so we've now taken the partial derivatives, and if you want to find the critical points, well, then all we have to do is we have to set this ugly thing equal to 0 and this ugly thing equal to 0 for the critical points, right? Now, this is kind of ugly. You can do it. So, like, you'll notice that this is, like, you can expand this out, and it's not actually that bad. If you expand this out, you just end up with a function with m, b, a system of two equations and two variables. You have m, b, they're all linear, and you can solve this pretty easily. So that is, of course, what you would do next. I am not going to do it by hand because that would take a really long time. But the basic idea is you set the partial derivatives equal to 0, and when you do that, you solve that system of equations. It's two variables, two equations, and they're both linear, and so it's not actually so bad to solve. And you end up with m is equal to about 4.11 and b is equal to 399.6, which were the parameters that we found earlier. Then the next thing you'd have to do is you need to check that the eigenvalues of the Hessian matrix are both positive. So then you take the partial derivatives again to form the matrix, and you check to see that it has positive eigenvalues at those 2 points, or at that pair of points. And I'm not going to do this, but you can work through it, and you'll find that it does have positive eigenvalues, and therefore this critical point is the local minimum, right? So you could use this test or to determine the d-test. You find that this system of equations has positive eigenvalues, and therefore that set of parameters minimizes S of MB. So that set of parameters has the minimum squared error. And therefore, the model f of x is equal to 4.11x plus 399.6 is the best fit line. And that is how you compute this. So a question for you all. So just answer and checking the eigenvalues. Yeah, so checking the eigenvalues, with, if they're both positive, then it tells you it's a min. If they're both negative, then it's a max. If one's positive and one's negative, then it's a saddle point. If any one of them is 0, then you don't know for sure, and you have to use other tests, which we haven't taught you. Okay, let me ask another question while we're here. So just answer in chat if you have a good sense of this. The question is, why can't we do this procedure with, with the mean absolute error? So why does this not work? So we were able to find a minimum of this mean squared error function using these tools. Why can't we do that for the mean absolute error? Let me go ahead and put my poll up again. Oh, yeah. So Jordan answered, can't find a derivative in the absolute. Yes, exactly. So the reason why it's a lot harder to do this for absolute value, for the absolute error, is because you can't, the derivative of the absolute value at the point 0 is undefined. And so because of that, you can't actually solve the mean absolute error problem using these multivariable partial derivative techniques. Instead, you'd have to do something a lot fancier. So if you end up taking a lot more numerics classes, you might one day learn about linear programming, which is not part of this class. And I should also warn you that the program in the term linear programming has nothing to do with computer programs. So just a forewarning. But yes, that's basically it. So this is why we don't, one of the reasons why we don't like the mean absolute error as much. is because the mean absolute error is a lot harder to find the minimum of, whereas the mean squared error, well, we can find the minimum of that just by using these tools from calculus. And yes, it gets pretty messy, but it turns out that we can solve that in general, and it's not so bad. So let's go back to where we were. So we were at this. So we found the best fit line, and it turns out that this procedure works in general. And so if we have a linear model, just in general, so if we're given, I'm going to switch to using x's and y's, just because that's a little bit more standard instead of h's and t's for height and time. X and y is standard, so you have some function f of x is equal to mx plus b, so a line with parameters m and b, where our data points yi are approximately equal to our f of xi with some error. So for example, we have the example we just showed, the x coordinates might be time, and the y-axis might be the height of a tree as a function of time. Well, then we have this mean squared error of the model, which is just this formula we gave a moment ago. And in order to find the model parameters that give the minimum mean squared error, we just need to consider this function s of m sub comma b equal to the mean squared error, and we need to find the minimum of that function. So it's still just a two-variable function, and so we just need to take two partial derivatives, and we can find the minimums of this function. And it turns out that you can, a moment ago, we sort of did it for a particular example with data. You can also do this in the abstract, and if you were to do this really carefully in the abstract, you'd end up with this very important theorem, which is if you have the same setup, we're going to let x bar be the average value of the x's and y bar be the average value of the y's. So x bar is the average value of the x's and y bar is the average value of the y's. Then what we can say is that the linear model that minimizes the mean squared error is given by this somewhat ugly formula, but it actually makes a lot of sense. So it's all the deviations from the averages, basically, multiplied together on top, and just the square of the x deviations on bottom for your slope. And you have your intercept is equal to y bar minus mx bar. So this looks a little bit ugly, but it's pretty easy, straightforward to plug in values and just find the averages and then sum all these things up. So this is something you can program a computer to do. And in fact, in practice, you would never do this by hand. You would just have a computer do it for you. So you can use either Excel, Python, MATLAB, or all of these tools have built in already the algorithms for computing all this based on a set of data points. Of course, this is a math class. That's MATA35. And so I'm just going to tell you what the proof involves. And you already have all the components of the proof, so it gets really, really ugly. So the proof just involves using the partial derivatives to find the minimum of this function, and that gets you precisely this answer. I'm not going to walk through it. I just tried writing it out last night a bunch of times, but it turns out that writing it out is super ugly and messy unless you have much fancier tools. So, and we don't have all the tools of matrix calculus in this class yet, so it's like actually deriving this is a little bit painful until you have those. But suffice it to say that you can use all these tools, and if you carefully carry it out, you end up with this theorem. And this basically tells you that when you have this data and you're trying to find a linear model, it's actually really easy. You just plug all the numbers into this into this theorem, find m and b, and that gives you a model that minimizes the mean squared error. And in the second half of class today, I'm going to be walking you through a very basic, gentle introduction to how you could use Python so that's a programming language, on a computer to solve these, to actually find these models, because doing them by hand is something that no one does now. Okay, and with that, I think it is exactly on time for the break, so I will see you all in about 10 minutes.